Thus far we've talked about periodic time-varying signals, or signals which repeated themselves. Now we want to talk about another type of time-varying signal that is not periodic. In fact, it represents a time or a function of where the voltage changes as a function of time, but it goes from one steady-state value to another steady-state value. This is sometimes referred to as a transient voltage or a transient response. A common place you'll find a transient voltage is with a capacitor in the charging and discharging of capacitors. So at this point in the class, we're going to introduce the concept of capacitance. You have a capacitor, and capacitance is a physical property of a device. Of a device that consists of two metallic plates or two pieces of metal separated by a non-conducting material. So you've got a conducting metal and another conducting metal, but they're separated by an insulator. Now if you apply a voltage to one of the plates and tie the negative terminal of the voltage supply to the other plate, you'll start to have current flow. And let's just take these one charge at a time. Yet the first charged particle comes and goes to where it hits the plate, but because of the insulator between the two plates, the charge isn't able to traverse the gap. But its electric field extends through the insulator and pushes a positive charge off to complete the circuit, but leaves behind a negative charge. And the instant we do that, we have then a separation of charge, which we now know to represents a voltage. There is a electromotive force, an electrical force, or a potential between those two plates now. As additional charges flow, we build up additional charge on the capacitor, and the voltage across the capacitor continues to grow. And it will continue to grow until it gets to the point that the voltage on the capacitor is equal to the strength of the voltage source. At that point we say that the capacitor is charged, or that the capacitor is full. Effectively what we've done is we've placed a bunch of positive charged particles on this plate and a bunch of negatively charged particles on this plate. And in effect, the plate, or the capacitor, is something like a storage compartment for charge. It's something like a bucket is for water. We'll talk about that in just a second. But imagine with me, if you will, that when there's no voltage on here, there's no pushing back against the source. But as voltage begins to flow, or as charge begins to flow and we develop a voltage here, there begins to be a voltage pushing back against the source. So initially, with no voltage on here, charged particles are free to flow very quickly. In fact, we sometimes refer to the capacitor as a short circuit under those conditions. When there's no voltage on here, we think of the capacitor as being a short circuit, and current through the depositing of charge on one plate and the charge continuing on from the other plate is able to flow without any pushback. But as soon as we start to get voltage across here, we get pushback, and so the current doesn't flow as rapidly, but it continues to flow, and it continues to build up the charge. The voltage continues to grow, which then pushes back more. So the current then has more pushback, and the current then is slowed down, and the current continues to slow down as the voltage continues to grow, until it gets to the point that the voltage on the plates here is the same as the voltage on there, and then no more current will flow. So initially, if we were to graph the voltage, and the current, it turns out, has the same shape as a function of time, initially it's growing very quickly, but then it becomes less and less and less and less until it approaches the source voltage V sub S. Now, as I mentioned, we can think of this capacitor as being like a bucket that holds a certain amount of charge or a certain amount of voltage. It's analogous to a bucket filled with water. Now, or a bucket that's capable of being filled with water. Now, imagine first of all that we don't have the hole in the bottom of the bucket. There is a plug in. There's a cork in the hole here. And imagine that the bucket is empty, and we connect it to an infinitely large bucket of water, a reservoir that has a certain height on it, but it extends for forever and ever, so there's no shortage of water at that elevation. If we now connect this big reservoir to an empty bucket, as you know, the water will start to flow in and the water level will start to increase. But as it starts to increase, there's now water pushing back against that, and so the water flows in a little less quickly or a little more slowly. As the water level continues to rise, the rate at which the water comes in becomes less and less until it gets to the point that the water in the bucket has achieved the same water level as the water level in our infinite reservoir. And as you know, water seeks its own level and can go no higher. So once it gets to that point, it can go no higher. And it started out filling very quickly and then filled slower and more slowly until it got to the point that it stopped filling completely. That type of a reduction in the fill rate that we are fairly comfortable with here is exactly analogous to the fill rate of a capacitor as we fill it with charge or as a voltage grows on it. Now, just as you can have the same water level in a smaller bucket and it simply takes less water to achieve that level, you can also have different size capacitors. And it turns out that the capacity of a capacitor to store charge is directly proportional to the surface area of these plates. So the larger the capacitor, the larger the plates of the capacitor, the more charge it can hold for a given voltage. And in fact, the way we measure the size of a capacitor is a ratio of the charge, the amount of charge that we can put on per volt. And that then becomes the definition of the capacitance, or the size of the capacitor, or the measure of the capacitor, and its units are farads. Now this concept of capacitance is much like resistance. It's just a physical property of materials, of matter. And just as we saw that resistance wasn't necessarily good or bad, or it could be good or it could be bad depending upon what you're wanting to accomplish with it, capacitors can also be either a helpful or a counterproductive quantity. We will add capacitance to circuits, and we will use capacitance in our lecture this week, or in our lab this week, to show how we can filter one frequency of signal from another frequency of signal, or that we can remove signals from voltage levels or signals from an overall signal that we're interested in, and leave behind the signals that we are interested in. Now, as I mentioned, the rate or the change in voltage on a capacitor as a function of time is described by an exponential function. And we'll use this very generalized form of function in our lab today. As you can see, it involves an exponential term with some constants multiplying it and adding it. This is meant to represent, say, x can either be a voltage or a current, but we can say then that the voltage or current on a capacitor is equal to the final value that the capacitor is going to attain plus a quantity of the initial voltage on the capacitor minus the final voltage on the capacitor times this exponential function. Now, you should be aware of what a discharging or an exponentially decaying waveform looks like. A capacitor that's discharging starts at some initial voltage, in this case 5 volts, and then drops off. It dries out. The charge initially flows very quickly, or relatively quickly, because there's a lot of charge in there. It's analogous to our bucket back here. When there's a lot of water, the water flows out very rapidly. But as the water level gets smaller and smaller, the rate at which the water leaves becomes less and less, until it gets to the point that there's no water left in there and no water flows out. This exponential curve describes that. initially the water leaves out or the charge leaves the capacitor very quickly, but as there's less and less charge in there, the rate at which the charge flows out becomes less and less, and we get to the point that there's no charge left and no current flowing, or the voltage decreases as charge decreases until it gets to the point that there's no voltage. Now, we will see that we don't necessarily have to discharge to zero. If we've got another power supply in there, we can go from one voltage to another voltage, and again, if it costs the capacitor, that transition will be described by an exponential function. Here now we have the final voltage being, say, -6 volts, the initial voltage being 8 volts, and we would have then the voltage across the capacitor as a function of time, this curve here being described as the final voltage, which is -6, plus the initial voltage, which is 8 volts, minus the final voltage, minus a -6 volts, times this e to the minus t over tau term. So that would then be -6 plus 8 minus a minus becomes plus. This would be -6 plus 14 times the exponential term. Now, as you know, when t equals 0, and we're going to just take a look at this exponential function for just a second. When t equals 0, e to the 0 is 1. So this term is just plain old 1, and we have -6 plus 14. That equals our initial voltage of 8 volts. This exponential term then dies out, making the amount that's being added to the final value less and less until this term goes to 0 as t approaches infinity. E to the minus infinity is 0, and we're left with then the final voltage on the capacitor. So this equation, or this formula, describes this action here in this waveform. And I should have pointed out on the discharging capacitor that this also describes that this function here describes this decaying waveform also. So let's go back and look at that. Here the final voltage is 0. So we'll have a 0 here and a 0 there. The initial voltage in this case was 5 volts. And we'll have then the voltage on this capacitor would then equal 5 times e to the minus t over tau, where this tau is called the time constant, and we'll talk about that in just a second. Now, similarly, this same formula describes this charging waveform, where the initial voltage is 0 and the final voltage is 5. So this is discharging, this is charging, starting at 0 and going to 5. Now we have the case where the final voltage is 5, the initial voltage is 0, so we have final voltage of 5 plus 0 minus 5 times this e to the minus t over tau. So this function here, this charging voltage, is given to us as 5 minus 5 e to the minus t over tau. And finally, we can go from some non-zero value to some other non-zero value, where the initial voltage here would be -5 volts, and the final voltage is 8 volts. And we have the final voltage of 8 volts plus the initial voltage of -5 volts going up to, or minus 8 volts times e to the minus t over tau. So we have +8 plus -13 times e to the minus t over tau. Now let's spend just a moment talking about this time constant value tau. It's in the denominator of the exponential. Now, in your college algebra class, you probably saw something like e to the minus kt, where this k, and possibly they even used r, where that constant was known as the rate constant. It had to do with the rate at which things were changing. It had the units of something per second or something per time. Tau, on the other hand, is known as instead of a rate constant, it's known as a time constant, and it has units of time. Tau becomes a measure of how quickly the circuit changes. In general, or at least for these RC circuits, tau is equal to the product of R times C, where R is the resistance of the circuit feeding the capacitor, and C is the size of the capacitor. So if we had a circuit with a voltage source and a resistor and a capacitor, that would be R and C, and that's our voltage source. The voltage on this capacitor would change more quickly for small capacitors rather than large capacitors, and it would change more quickly for smaller resistors than larger resistors. Or to put it another way, the larger the capacitor is, the longer it takes for it to charge. Or the larger the resistor is, the longer it's going to take for the capacitor to charge. So the time constant is equal to the product of R times C, and it will take longer to charge by we can make it take longer to charge by either increasing the resistance or increasing the size of the capacitor. And again, this tau is known as the time constant. And so a small tau means that it's going to charge quickly. A larger tau means that it's going to take longer for it to charge. But tau is a very interesting number. We're not going to go into a lot of detail on it. Simply but let us say that tau becomes a measure of how quickly it will change, and it's equal to the product of R times C. And when we have gone through one time constant, when the capacitor has been charging for one time constant, it will be at about 38% of its it will have gotten to, let's go back. We're talking about a discharging capacitor now. When we have allowed the capacitor to discharge for one time constant, it will have discharged down to about 37% of its original value. After two time constants, this is for 1 tau, for 2 tau, or we've allowed this capacitor to discharge for 2 time constants, it will be down around 12% of its original value. After 3 time constants, it'll be down to about 2% of its original value, and by the time you get out to 4 time constants, the capacitor will be down to less than 1% of its original charge. Now, this exponential function theoretically never goes to 0. It approaches the time axis asymptotically. But generally speaking, we'll say that after 4 tau or 5 tau, it's close enough to 0 that we don't worry about any residual charge on it. So to recap that then, tau becomes a measure of how quickly things change. For example, if tau equaled 1 second, and we had this capacitor here and we were going to allow it to discharge, after 1 second, it would be down to 37% of its original value. After 2 seconds, it would be down to about 12%, 3 seconds it would be down to about 2%, and after 4 seconds, or 4 time constants, it would be down to less than 1% of its original value. On the other hand, if tau was, say, 1 hour, in other words, the product of R times C was 1 hour, after 1 hour, it would be down to 37%. 2 hours, it would be down to about 12% of its original value. After 3 hours, 3 tau, it would be down to about 2% of its original value. And after 4 tau, it would be down to less than 1% of its original value.